At the end of the last video, we talked about how we have to be really careful if we're thinking that taking a limit is identical to just plugging in the values that x and y are approaching. That sometimes works, and you might recall that happening on occasion within Calc 1, but in general, that is not what is happening with a limit. Remember that a limit was all about what the x and the y values are approaching. They're approaching 0, 0, and we're going to be seeing what z-coordinate everything here is approaching. So let's take a look, though, at when exactly you are allowed to simply just plug in your values of x and y. This is going to bring up a concept that we talked about previously in a Calc 1 class as well. So we need to introduce the concept of continuity. This concept of continuity is massive. We're going to be talking about continuous functions all the time, just like you did back in a Calc 1 class. So when we're dealing with a two-variable function, what does it mean to say that that function is continuous? Well, we're going to have the same definition pretty much that we had back in Calc 1, but also that we had in the last chapter when we were using this, or when we talked about continuity of vector functions. Here's the idea. A function of two variables is continuous at a point if when I do the limit as my x comma y approach an AB. So again, that means like as I'm kind of approaching the AB and I'm looking on the surface, what z value am I inching towards? Is that actually equal to the z-coordinate that the function produces? So there's kind of like an implied question mark here. Again, we're comparing the left side and the right side and seeing if they match. Okay. We say that if if f is continuous on D, so like some collection of points, then we'll say that it's continuous on D if it's continuous for every point within that set of D. Okay. So intuitively, the meaning of continuity is that if the point xy was to change a small amount, then the value of f of xy, the z-coordinate, would also have to change a small amount. So like if I was to draw a surface that maybe went like this, right? It's kind of got some like rolling hills to it. If I had a surface like this, notice that if I was to start at a point, it's got some particular z-coordinate associated with it. But if I was to go ahead and kind of bump that point a little bit to the left or the right or forward or back on the surface, but just a small amount, the height is going to change by also a fairly small amount. Okay. This is different than if I was to look at like a type of surface where maybe there was a break or a gap. So like imagine a surface that has like a jump to it. Maybe something like this where I have kind of two planes, but one that kind of stops right here and another that picks up kind of at the same spots just a little bit higher up. Well, now notice that if I was to maybe say pick a point over here, and then if I just nudge that point a little bit over to the right, it's going to jump up drastically really, really quickly. So a function like the bottom one here is not continuous, whereas the function up top is continuous. Functions that aren't continuous in two variables are going to have things like holes in them, or breaks, jumps like this, things like vertical asymptotes, and there are going to be things that ultimately kind of end up not being connected in some sort of a way. Okay. So what we really want to focus on is what types of functions are going to be kind of in this nice continuity camp, and what functions are going to be bad and not continuous. Okay, well, to understand that, we have to take a look here at this important next definition. What is a polynomial function of two variables, and what is a rational function of two variables? All right, well, a polynomial function of two variables is a function that's built from terms that have the following shape. Here, c is a constant, and m and n are going to be non-negative whole number values, or non-negative integers. So things like what I have down here, 1 times x to the third y to the first. Things like -2 times y to the first x to the first, or 3 times x to the 0 y to the 0, or y to the 2, or maybe do like -1 times x to the first times y to the 0. Things like this, if they're added and subtracted together, are referred to as polynomial functions with two variables. Okay. They're very similar to polynomials that you would have had back in, again, a Calc 1 or a Calc 2 class, but now you're allowing for a mixture of x's and y's to occur together. A rational function is really just going to be a ratio or a division of those two polynomial-like things. So you can see here I have something polynomial up top, something polynomial on the bottom. So this creates a rational function. So what's really nice about these sorts of functions is that the extension of limit laws immediately implies, so those limit laws that we had up above, if I applied them to these functions, what we would find is that they work all the time, and these polynomial functions are continuous on all of R2. That is, on the entire xy plane, polynomial functions are always defined. And rational functions are going to be continuous as long as their denominator isn't 0. Okay. What this means is that we can evaluate limits very, very nicely, because take a look at what the continuity function or continuity definition says. If a function is known to be continuous, then the limit is equal to f of ab. So if there was no question mark here, I knew a function was continuous, say like this function right here. And then you said, what's the limit as you approach 1, 2? Well, then you would just say, that's awesome. Because it's continuous, I know it should be equal to f of 1, 2. That's the same as just plugging in 1 and 2. So remember, I said back here that we can't just plug in 0, 0. That doesn't work. But I can plug it in if I already know I'm working with a continuous function. And right now, polynomial functions and rational functions are continuous.